which is not published or is only partly published, creating ensembles to a limit. Dot, dot, dot. Okay, so what is it that, what is our goal? Let me try to say. Uh, so our goal is the following. We would like to produce maximally entangled states of many particle systems. Entangled state. So first of all, then I have to explain what is an entangled state. So the experts in the audience may please forgive me for this introduction. But before I go on, Professor Senthil, how much time should I, you know,
A maximum 1.5 hours, so you can go up to one
up to
maximum.
one? Okay, thank you very much. So the simplest setting for entanglement is a bipartite setting, which means that there are two particles. You can imagine two electrons in the helium atom or whatever it is. Okay, so there are two particles, and they are in a joint state, quantum state, which, as you know, we represent by this vector in a Hilbert space psi. And a state is unentangled. Let's say that these two particles we label A and B, they are unentangled if this joint state of A and B, it can be written as a state of A and a state of B. That is, it's a tensor product representation here. So individual subsystems can have pure states. In that case, you would say that the state is unentangled. Whereas if you cannot do that, any entangled state is not entangled. I mean, it's not unentangled. Okay, so the simplest is unentangled state. So operationally, what it means is that subsystems of joint states can be described by pure states, which means that there exist measurements whose outcome you can be absolutely sure about. So, example of a state which is not of this kind is, for example, if you take two spins and they are in the spin singlet state, then if you ask the question, well, is spin 1 or spin A up or down, there is no answer to that question. What is the state of the subsystem of spin 1? If you calculate its reduced density matrix, you will get half 1, 0, 0, 1. So it will be maximally mixed. So in fact, these states will be mixed states. Subsystem states will be mixed if the state is entangled. So here is an example of an entangled state. Okay, so it's a superposition clearly of these unentangled states themselves. So each of these states is unentangled, up, down, down, up. It's a superposition of these unentangled states which can create entangled states. But not all superpositions are entangled. For example, if you have up, up, plus, down, down. This is also an example of an entangled state. But also up, down, plus, down, up is an unentangled state because it can be written as up, plus, down, tensor, up, plus. Okay, so in a rotated system, they are just a tensor product of these two. So these are also unentangled states. So in general, if you consider a general thing, we have a Hilbert space dimension D, another Hilbert space dimension D. So this is for subsystem A, subsystem B. So I'm taking equal dimension in both of these subsystems. Okay, so you can consider a D level atom, another D level atom, D levels, another A and B. A general state of this is given by this Cij, Ij, where Ij can go from 1 to D. So this is a general state. And when will this be an entangled state? Is determined purely by the properties of the reduced density matrix of this state psi. Okay, so if the reduced density matrices are maximally mixed, that is, if the reduced density matrices are proportional to identity, d by d identity, then the state is maximally mixed. If rho A is proportional to identity, then it is a maximally mixed state or maximally entangled state. So maximally entangled states are characterized by maximally mixed subsystems. Physically, what you should take away from this is that if you have information only about subsystems of maximally entangled states, you have no information or minimal information about the entire state. Okay, so information is spread out. You need all the you need information, joint information, in order to describe the state. So mathematically, how does one get this reduced density matrix? Sorry. Uh, there was some disruption. Sandil, are you seeing
Yes.
my?
Yes.
Okay. Yeah. Yeah.
I'm
Okay.
seeing the board.
Now I think. Yeah. Yeah. Now. Yeah. So the how does one get this reduced density matrix rho A from the state psi? Okay. So let us describe that. So formally, you can take a density matrix of the state and then trace out, let's say, subsystem B, you will get the density matrix rho. And also wise the other way around, you can interchange A and B and you can get also rho B. Now, in terms of this pure state psi, there is a very simple way of writing this. Psi, Cij, Ij. This is any basis. We have taken this Ij to be some arbitrary basis, orthonormal basis. Okay, so I prime is delta I prime, etc. How does one find rho A? It's a very simple procedure. We take the C, you can see that this is equivalent to the following. Rho A is C times C adjoint, where C adjoint is the usual thing, Hermitian adjoint. Okay, so this is the thing. So uh, from this matrix Cij, you can consider now these coefficients as a matrix of coefficients. From that, you can get the reduced density matrix by simply calculating CC adjoint. You see that this is now a guarantee to be a positive operator. And from the normalization that modulus Cij whole square summation over all I and j is 1 implies that trace of this density matrix is 1. Okay, and positivity is guaranteed. So you see, all you need to do in order to find out if the state is maximally entangled, it's not clear from from just these coefficients whether that is the case, but if it is maximally entangled, then rho A should be identity by D. If psi, let me again go back to AB, psi AB is maximally entangled, let me call it ME, okay? Um, then this is the case. So, but this has got to be CC adjoint. See, so basically this CC adjoint must be identity. And in fact, you can also look at the other density matrix rho B, and that will be equivalent to requiring that C adjoint C also be identity by D. So what does this mean? It means that if you have if you have a matrix such that U adjoint is identity and U adjoint U is identity, it means that U is unitary. We have almost that case except for this D here. So it means that square root of D into C is unitary. Okay. So So that means that we can write a maximally entangled state as 1 over d summation uij ij, where this I and j going from 1 over to t, where this is any unitary matrix. So what I want to get from this step that I'm doing is that it's possible for us to take any d by d unitary matrix and construct from that a maximally entangled state of a d into d system. Okay, so this is the basic step. I hope this is clear, and in fact, it's a one-to-one mapping. Every unitary matrix, so there is a connection between a unitary matrix and maximally entangled state. So these are maximally entangled. Okay, so there is a one-to-one connection between these and this is a kind of a reflection of what is generally called a Choi. Jamiolkowski isomorphism. This is a special case of that in the sense that there is some connection between an operator and states. Here the operator is this unitary operator that I'm talking about, and here is a state, that is this bipartite state of two particles. Okay, so now I will not go into why we are interested in creating maximally entangled states. So that's a large issue in quantum information. There are many nice protocols like teleportation, which depends on the creation of multipartite or this kind of maximally entangled states, dense coding. So the uses of entanglement is quite a lot in quantum information protocols, and therefore it's useful to construct these states and know how to have them. Okay, so are there any questions at this point? Should I continue?
So for belt states, how do you construct this unitary matrix? Is it possible?
Yeah, so every state will be, so in that case, it's simply the identity.
Yeah. Okay.
It's just proportional to identity, 1 over root 2. Sorry, again, my.
No, something is. Yeah.
Now it's, yeah, what about now?
Yeah, it's clear now.
Yeah, this is this is what I teach on. Yeah, so you were asking about so in fact, let's write down a general Bell state. So 1 over square root of d I. This is a canonical maximally entangled state. Okay, I is 1 to d. You see, there's perfect correlation. If the subsystem state is I, the other subsystem is also I. Okay, so this is a maximally entangled state in d-dimensional space, and the matrix that I was talking about, U, is simply the identity matrix, which is of course a unitary matrix. Okay, so any other questions? So now, yeah.
What is this trace B, trace A you have written?
Where?
Yeah.
Here, this is partial trace over subsystem B.
You have system A and B, and
I'm tracing out subsystem B.
okay.
So, if you want, let me just do it explicitly. So, if I write the full density matrix, I'll have Cij, C star I prime J prime, Ij I prime J prime. Okay, Ij and I prime J prime. Now, when we do a partial trace over B, that means that we basically we need to contract J and J prime. J is equal to J prime. Okay, so this becomes then summation Cij C star I prime J I prime this is the density matrix, rho A, summation over I prime, and J. So now you see this is nothing but C adjoint I prime, I prime. So that's why you get rho A to be C adjoint. Okay?
Okay, okay.
Yeah. So any other clarifications? So now we come to, and so it's all very clear when one deals with bipartite pure states, the situation is very clear. In fact, although I have been talking about maximally entangled states, you can say, okay, let me not consider maximally entangled states. What can you say about the state in general? The answer comes from the so-called Schmidt decomposition, which is a representation like this, where this is lambda j's are positive numbers, and they are called the Schmidt eigenvalues or the Schmidt values. And these form orthonormal bases in respective spaces A and B. Okay, so what we are doing is basically finding rotations from these arbitrary orthonormal bases ij to very specific orthonormal bases phi aj, phi bj, but they are still subsystems orthonormal states, such that this sum is only a single sum, you see, from 1 to d. This is 1 to d. So this is a d square terms are there, whereas here there are d terms. So in general, the entanglement of this is measured by these states here. Suppose this lambda j, these are all eigenvalues, these are all positive numbers, so we can write them, arrange them like this, greater than or equal to decreasing order. Now, now, a, if lambda 1 is, by the way, these lambdas from normalization, they sum to 1. Lambda j is 1. So they are like exactly like probabilities. Okay, they are positive and they sum to 1. And if lambda 1 is 1, everything else must be 0. Then the state is unentangled. Okay, and if and only if all of them are equal, lambda 1 equals lambda 2 dot dot dot, lambda d is 1 over d, then it is maximally entangled. So that is the case that we have been considering so far, and that corresponds to simply all of theseCij's, the Cij being proportional to a unitary matrix. That's because these lambda j's, they are coming, they are nothing but the eigenvalues of rho A or rho B, both are equal. Rho eigenvalues are equal. Right. So in general, there is a situation between a probability distribution which is peaked at 1 and an equal probability distribution of everything between unentangled states and maximally entangled states. So in between you can measure entanglement by various measures. So for example, one of the measures is 1 minus lambda j squared 1 to d. This is called linear entropy of entanglement. Linear entropy of entanglement in this. Okay, 1 minus this. So the maximum possible, so this ranges from 0 when this is unentangled and you have only one of them to be 1, to when it is maximally entangled, it's 1 minus 1 over d. Another very important measure is the von Neumann entropy, which is considered to be the measure of entanglement, is simply minus sigma lambda j, is the Shannon entropy of the Schmidt values. Okay, so this will range from to log d. So for example, maximally entangled state is log D. Okay, so in a log 2 base, it's log 2 D. So for example, for a Bell state of 2 qubits, it's simply 1. Okay, so we have all of these things with us. Now I want to, we understand these very well. What it is that is interesting is when we go beyond 2. Beyond 2 particles, for example, if we have 3 particles, then many of these constructions don't go through. We have a general state to be this tensor Cijk ijk. Let's take again for simplicity, all of them are equal to space. All of them are equal to, I mean, they are all quantum systems, dimension D, equal. So that's the simplest one. We can generalize it, but that just adds complication which we are not interested at the moment. For example, the state up, up, up of 3 spins plus down, down. Okay. So this is an example of such an entangled state. If you want to normalize it, this is called a GHZ state. And it is an example of something which looks very entangled, maybe even maximally entangled. But what exactly do we mean by maximally entangled in this case? For example, another example of a state which is entangled is a famous example is this state, which is called a W state. Okay, now these two are very canonical examples of 3 qubit states, but they have very different entanglement properties. And in some sense, the GHZ is considered to be maximally entangled, but W is not. Okay, and it's a very interesting situation which there are some directions in which I will not go into about going from bipartite to genuine tripartite entanglement and so on. But what are the problems? But first of all, let us try to define a maximally entangled state in a very similar way to which we have defined maximally entangled states of bipartite systems. So when we try to do that, what we will have, we'll have, let's say, 3 again, Cijk ijk. If we have access to only subsystems, so this is what we did in A and B when we have 2 systems. We said it's maximally entangled if the subsystem rho A is maximally mixed. So if you have access only to subsystem A, you really have no information at all, nothing. You have like very democratic information. It's pure white light if you're from optics. So or pure noise. So we might try to do some similar thing. We have A, B, and C. We can say that maybe rho A has to be identity, and similarly rho B has to be identity, and similarly rho C also has to be identity. Maybe. But you see, there are also further subsystems now. I can have A, B. What should I do with this? Can I require this also to be identity? But now it is a D squared dimensional identity. Okay. So is this possible? ID by D. Okay. So this is, so is this possible? Is this needed? So it turns out that this is not possible, for example. Okay. In a pure state, we cannot require something like what I just wrote down, because of a very simple reason, not hard to understand at all. The eigenvalues in this bipartite case of the reduced density matrix rho A, the eigenvalues, so the spectrum is the same as the spectrum of rho B. And that constraint is coming because you're starting as from a pure state and finding these density matrices. The same constraint holds here. So the spectrum of rho C must be the same as the spectrum of rho AB. Now you can see here that these are all, they're having different spectrum, and so this is not possible. This is possible for sure. Okay. So in fact, this is all that is required in the case of Q trits, or particle system. This is all that is needed for the system to be considered to be maximally entangled. Okay, and how do you find out these reduced density matrices? You do the same thing. So, like for example, suppose I want to do this. I want to find out reduced density matrix for A from the ijk. So we do the same thing. Suppose this I is referring to, the first index is referring to A, this to B, and this to C. What we are doing when we are doing an A versus BC split, so we could consider the tensor like this, ijk, and consider this as an array which is D into D square dimensional array. So now it's not a square matrix anymore, it's a rectangular matrix, D square. And then CC adjoint is a D matrix. In fact, this is the reduced density matrix of rho A. Okay, and the spectrum of this should give you the should give you the entanglement of A with B and C. And if you want this to be maximally mixed, you want this to be proportional to identity. Okay, so this cannot be a unitary matrix now, but we require this to be a so-called isometry. So it's just a generalization of a unitary operator. CC adjoint C need not be identity, but CC adjoint has to be identity. So so when you get out into multipartite systems, there exist many types of entanglement, and we can define an absolutely maximally entangled state in the following way. Okay, so let me take, actually the 3 is an odd number. Let me take 4 because that gives us more control, and actually it is related to what I want to talk about. 3 is not that difficult or different from 2. A, B, C, and D. Okay, now we have 4 particles, and we call this an absolutely maximally entangled state if rho A is same as rho B, same as rho C, same as rho D, is maximally mixed, ID by D. Okay, and not only that, if you look at any 2 of these subsystems, you don't still get any information about the state. So that means that rho AB should be, now what are the others? Rho AC should be rho BC, should be identity by D squared. You see, we don't have to now worry about other density matrices. For example, rho AB. No, AB is taken into account. So, for example, BC or AD. Okay, rho AD will have the same spectrum wise. It's the same spectrum as rho BC because the entire thing is in a pure state of 4 parties now. Okay, so we don't have to consider the other 3 density matrices. For example, rho BD is same as spectrally AC, etc. So we have to require these conditions. Okay, so indeed, actually, it is sufficient for us to require only these three conditions, because this implies this. After all, if rho AB is identity d by d squared, you can always trace out B to get rho A, and that will be identity by D. Okay, so there is information about these reduced density matrices rho A, B, and C from these bigger states rho A, B, rho A, C, and rho B, C. So my point is, if you have a four-party state like this, to test whether it's maximally entangled, all you need to do is look at these three two-particle density matrices and see if they are maximally mixed. If they are, then the state will be considered to be absolutely maximally entangled. Okay, this is there is no information which is coming from subsystems, and you can easily generalize this to any number of particles that you want. Uh, so now let's write a general state C I J K L I J K quantity. Okay, so now what do we require for this state to be absolutely maximally entangled? AME states. What are the requirements on this tensor CIJKL? It's very similar to the unitarity conditions. In fact, it's a generalized kind of unitarity condition. So um, I'm going to say that this um, uh, I guess I can write this down as 1 over D UIJKL IJKL. Okay, where this matrix UIJKL has to be unitary if I group these indices like this, IJ versus KL. This will be corresponding to the grouping ABCD, because A and B correspond to the indices I and J, and CD correspond to the indices K and L. They refer to the K and L indices. Therefore, if I consider this grouping IJ together, that is like corresponding grouping A and B together and K and L CD together. Okay, so each of these will give me a D square array. So this will be a D square into D square matrix. It's a D square by D square matrix, and this has to be unitary. If this is unitary, then the entanglement of rho AB will be maximal, or rho AB itself will be identity by D square. If, yeah, is there a question?
Yes, in the chat box.
I'm sorry, I can't read.
Okay, can I read?
Yeah,
okay.
please.
Sir, what does physical meaning of spectrum of states rho AB equal to spectrum of state rho BC?
Well, the mathematical meaning is that the eigenvalues are the same. Okay, the
Shall,
huh?
yeah. So shall I ask him to speak?
Yeah, please.
Prashant Singh, are you able to? No, he's not able to. That's why. Yeah.
Yeah,
Yeah. Physical meaning of spectrum of state rho AB equal to spectrum of state rho BC. That he wants.
There is some noise. I think maybe he should mute. Yeah, so, well, the mathematical meaning is clear that the eigenvalues are the same, and the origin of this is coming from the fact that you have this overall state to be pure. Okay, this larger state to be pure. Now, there are clearly implications of this, but its physical meaning, I don't know. how to whether there is something which is further implication of this. Okay, I mean there is. You see, there are various ways of looking at it. One of the ways is, I would say that the physical meaning of this is that the overall entropy is zero. This is also related to the fact that the overall state is zero. You see, so any subsystem, because entanglement is closely related to the physical quantity of entropy. So when you ask what is if the spectrum is the same, it means that the entropy of subsystem A is same as entropy of subsystem B. Okay, so in that sense, this is like this is yeah. So
He said he could get it now.
okay, very good. If Sai or any quantum information expert has something to add, please. I think it'll be nice. We can add too. Okay, if not,
There is one more question from Miss
yeah,
Sita.
sure.
No, your side is very noisy. You see, your side is very noisy. Yeah,
Yeah, unfortunate, yeah.
unfortunately.
But
What is
is
your,
the chat box?
what is your question? You see, can you put it in chat box, sir? No.
Okay.
You continue. Yeah.
Yeah,
See,
yeah.
why we are not considering spectrum of rho dB or rho DC?
Okay, let me go back to the previous slide. Oops. Yeah, Senthil, am I in the right page now?
Yes, yeah.
Yeah. So the question is why we are not considering AD, etc. But that
dB
is
or
why
DC? Rho dB or rho DC?
rho dB.
Or
Yeah.
rho,
Oh, rho. But rho dB is same as rho BD in a sense. Okay. I mean, right. So AC, when I consider CA, this order doesn't really matter. I, I I don't know if that's the question. If that's the question, that really doesn't matter. If you are putting their indices first and second, they are related by the so-called swap operator, which just they interchanges them. So physically, it's not the same. It's the same. So, but if you are looking at the other things like AD, etc., as I said, it's the same as the spectrum of BC. Therefore, we don't need to. If this is maximally mixed, then so will also be BC may be maximally mixed. Okay.
is it clear, Nisi? Say yes or no. Yes, yeah. See, she understood. It seems.
So Arul, you are considering only finite dimensional Hilbert space here.
Yes.
Is that correct?
Yes, Professor Lakshmi. Yeah. So we are considering only finite dimensional. Infinite dimensions, unfortunately, even to define a maximally entangled state would be difficult because you will have all infinite eigenvalues.
Essentially, you are considering the spin space, I suppose.
Yeah, any finite dimensional Hilbert space. Yeah.
Yeah.
It can be spins or any finite atomic number of levels and so on.
Okay.
Yeah. So now this is where things start getting interesting. So we have this object Cijkl, which is defining this four-party state, and I said that I'm writing it like this. Then this matrix Uijkl must be unitary, so that AB is maximally entangled with CD. But now, for it to be absolutely maximally entangled, other things also have to be this thing. So if we consider AC, that should also be maximally mixed. So, but what does AC, considering AC means? It means considering this I and K together as a group. Okay. So that means that IJKL, I'm going to consider this I and K together and J and L together and write this as, let's say, UR, or what should it be? Is it UR? No, it's UT. Oh, maybe I call it UGAM. Maybe I will uh, U U gamma K J. Uh, yeah, I think this is fine. KJ and IL. Okay, so what we have to do is we have to group this IK together and JL together. So that's equivalent to, suppose we define this matrix U gamma whose KJ element, KJIL element is precisely equal to this IJKL. Okay, then we should require that U gamma be also unitary. So let me actually write this out properly here. So U IJ K, well, maybe I rewrite here A B C D. So so we had I A. Let me write it in terms of these. I'm putting these indices, okay, so that we write it more clearly like that. I C I D. Okay, so this is what I wrote first as U I J K L, and I was looking at this as this D squared by D squared matrix, and I was saying that this has to be unitary for AB versus BB maximally mixed. Okay, now we are going to require that AC be maximally mixed also. So what does that mean? So that means that we have to look at uh, AC together. Okay, so for that, IA, IC, UR, IB, ID. Okay, so AC is now clubbed together and BD is clubbed together. I'm calling this matrix to be UR. That is, this matrix element should be exactly that's equal to this. Okay, so now I'm calling this matrix UR. UR is such that IA, IC, IB, ID is equal to this element here. You see that it's a rearrangement of this unitary matrix U. Okay, and that is a particular rearrangement which is called UR. It's also called realignment. So what has been done? What has been done is just the interchange of these two indices here. Okay, and this operation actually first appears. Uh, I don't know whether it first appears, but it appears in a context of quantum open systems as a connection between dynamical matrix and Liouvillean. So it's got some other origins, but it's some operation which appears pretty often in quantum information theory. And therefore, what we require is that you are also unitary. So U is unitary implies that rho AB is maximally mixed. UR also is unitary implies that rho AC is maximally mixed. But that's not all. We have one more, namely AD. This should also be, or BC. Okay, it doesn't matter. AD or BC. So what is that? That is the grouping of A and D together. So IA, ID, U, let me call this gamma, IC and IB. So this is now the definition of the array U gamma, which is also equal to this. Okay, and now we require that if U gamma is also unitary, then it implies that rho AD is maximally mixed. So now when we go from 2 particles to 4 particles, we can therefore use these conditions to define what are called absolutely maximally entangled states. So this generalizes the notion of a Bell state to 4-party systems. And it is given by this peculiar object, which is a 4-index tensor Uijkl, which defines the state. You see, this 4-party tensor defines the state of 4 particles, but a state this state ABCD will be called an absolutely maximally entangled state if it satisfies the following properties. U is unitary, d square by d square, where this U is considered as Uijkl. Okay, so this is how we are looking at that, and but this is not the only condition. UR is also unitary, and this UR is IL versus KJ, and U gamma is also unitary, which is UIK and JL. Okay, so in fact, these are the only pairings of these indices that are required. This is called a partial transpose, which is a well-known operation in quantum information. It was used by Perez to detect entanglement. So this is just interchanging the subsystem, these two things. So if you can look at it as if it's a partial transpose on a d square dimensional system. Okay, so if all of these rearrangements of this unitary matrix is unitary, then this defines an absolutely maximally entangled state of 4 parties. Each local dimension is d. So this defines what's called an AME 4D state. And this is also variously called, it has been also called a perfect tensor. There is a whole lot of literature on so-called tensor networks where people join a lot of these tensors in one larger array, and there are useful properties of these things which is defined by this perfect tensor. So there are various terminologies. So U is, in this sense, it's called a multi-unitary matrix, because it's not only unitary, but various rearrangements of it are also unitary. And in particular, if U is unitary, its realignment is unitary, and its partial transpose is unitary, it's also referred to in the literature as a 2-unitary. This 2 is coming in here to indicate that every subsystem of size 2 is maximally entangled. Are there any clarifications?
No, I'm not seeing any doubts.
Okay. So yeah, so this may appear a bit, so let me explain with regard to 2 qubits. Okay, so that is D is 2. I'm sorry. This is not really well. I don't know. See, when I come to this color thing, I don't know how to go back. Okay, let's consider the case of 4 qubits. Okay, so that is D is 2. this U will be a D square by D square matrix, a 4 by 4 matrix U. Okay, so you can take an unitary operator in 4 dimensions. Okay, and write this like this. So it's a 4-dimensional 4 by 4 matrix. So there are 16 entries. Those 16 entries go into creating this 4-qubit state CIJKL, IJKL. Okay. Now, how does one find these other matrices? UR, for example. What you do is you take this matrix, this submatrix, 2 by 2 matrix, which has 4 elements, and you make it one row. Okay. You take the second 2 by 2 matrix, make it the second row. So this is 1 made into row, 2 made into row, 3. What does it mean made into row? A, B, C, D made into row is A, B, C, D. That's all. Okay. So that is just a reshaping 3R. You can do all this very well in Python 4R. So this is what the realignment is. So this is a crazy operation. It may, or there is no need that if this was unitary, UR be unitary, but that's what we should require. And U gamma, there are various, there are again 2 ways of doing it. One way is simply to take transpose of the first one. First block, full transpose. We know how to do that. 2 full transpose, 3 full transpose, 4 full transpose. Okay, so this will be U gamma. So we are doing partial transpose means we are doing blockwise transpose. Okay, and that should also be unitary. So in fact, it turns out that no such matrix exists for D is 2. No 2 unitary exist in D is uh, for n is 4. That is, no army for 2 state exists. So this has been known for some time. It goes back to a work of Higuchi and Sudbury. How entangled can 2 couples get? That's the name of the paper, and they show that there are too many constraints. Basically, they show it in a different way, but it is equivalent to showing that there exists no 4 by 4 unitary matrix such that both UR and U gamma are also unitary. Okay. So there are, if you take 4 qubits, so let me just rephrase this thing. Again, if you take 4 qubits, 2-level systems like this, it is not possible for you to have a state such that this is maximally entangled or maximally mixed, that is maximally mixed, and that is maximally mixed. So no army for 2. However, there does exist army. You can have 5 qubits. It exists. 6 qubits exists. 7 qubits does not exist. In fact, it has been shown, this has been shown 3 years ago, but it has been known for some time that no army state exists for any of these things. Army 8, 2, and so on do not exist. Okay. So, but what about 4 parties, but higher local dimension, like Q-trits? It exists. 4 parties for 4-level systems exists. In fact, it was known from earlier work that AME exists for all 4 parties apart from qubits. Doesn't exist. Except 4, 6. There was a question mark on this. Everything else exists. D greater than 6 exists. Okay, there was a question mark this was an open problem for a long time. We settled this recently as exists. Okay, so you can see this in an archive paper. This one actually is a bigger, involves more authors than Suhail and Suhail. Arvinda is not there. So this is a paper with Suhail and the group of Karol Szyszkowski in Poland. Uh, and how we showed that involves actually a dynamical system. So, uh, that's what I wanted to actually talk about. In the where is the nonlinear map in all of these things that I'm talking about? So that's where I'm tending towards. And so let's actually look at one particular thing. We have a unitary matrix, d square by d square matrix. Okay, let's look at IJUKL, and let us also look at its realignment as the matrix uh, such that this is equal to, hmm, again my can't erase too well, IKURJL. Okay, so let us first try to find out a matrix U such that this condition is true. That is, UR is also unitary. Okay, U is unitary as well as, so belongs to unitary space in D square, as well as UR also belongs to unitary D square. In fact, there is a whole literature in physics which has developed, they call this dual unitary. Independent of this, they call this dual unitary because of constructions of many body quantum systems. They found that these things are solvable in some sense. So that will be another lecture in itself about using these unitary operators as building blocks for larger quantum many-body systems. But let me just say that this is also used very much. You can look at, again, our papers are there, but the first papers of this come from the group of Prosen. They are the ones who call it dual unitary because of some space-time duality. But let me uh, let me now just ask: how can we create unitary operators such that their realignment is also unitary? Creating unitary operators is trivial. You just take any d square orthonormal basis and you put them in here. That creates for you a unitary matrix. However, I mean, that's not the only condition, but that's that's pretty much it. However, the condition that this realignment also be unitary is a peculiar condition. Uh, so what we did was the following: there is an algorithm, which is a very simple algorithm to describe. It's in some sense very naive. So you take U, and then you find out what is a realigned operator. Okay, the realigned operator is not necessarily unitary. In general, it doesn't belong to the unitary operator set. So you want to find out the nearest unitary. Okay, call that, let's call this U0, call that U1. So the key step is this nearest unitary. And then you do realignment of this. It will not be unitary. Find out its realignment, I mean nearest unitary, U2, and so on. So you iterate this, maybe you will be lucky such that this actually converges to something where both U is unitary, and so UN such that as n tends towards infinity, such that UN is unitary, so also is UNR unitary. So this is an algorithm which is published in that PRL. This is the nearest unitary, is a simple thing to calculate. So how does, if you take any matrix A, how do you find the nearest unitary? The nearest unitary is got by either two things. One is called single value decomposition, other is polar decomposition. So let me call it from the polar decomposition viewpoint. You take any matrix A, if you write this as, we use the letter V here, V times some H. You can write this as V times H, where V is unitary and H is positive, positive definite or positive semi-definite operator. Okay, so this is called a polar decomposition. And this is equivalent to, I mean, you should think about this as a generalization of any complex number can be written as a real positive number times of pure phase, e to the I theta. Polar decomposition is simply a generalization of this idea to matrices, and this V is actually the nearest unitary to A. Okay, so this is the known from linear algebra. You can go back and find out proofs of this, but it's a very useful thing to have. So now all we need to do is implement this algorithm, and this turns out to be a nonlinear map. So now if you look at it in terms of dynamical systems, what is it that we have? We have a map from unitary operators to unitary operators. And this map is a nonlinear map because of this polar decomposition step. This itself is a linear map, but this one is a nonlinear map, and this we have shown in some ways that this converges, that it converges in general to a dual unitary operator, but not in general. In fact, there's an open problem. But we have shown that for the case of qubits, d equals 2, the algorithm, the fixed points of the algorithm are all dual unitary. And we have shown convergence of this. And so we call such a map an MR map in this. So MR map just takes a unitary operator and returns a unitary operator from this. Okay, and iteration of this we claim produces dual unitary such that U is unitary and its realignment is also unitary. How much time more, Sandhya?
You have 15 minutes.
Okay. I think I will wind up shortly. So this will give us this this thing. There is a very nice thing for qubits. You see, although qubits states don't exist, dual unitary certainly exist, and there is a generalized thing for dual unitary. So one thing which I did not mention in all of these things is that if U is dual unitary, then U1 tensor U2 local uh, unitaries can be applied to this is also dual unitary. Okay. This this property is, in fact, this is telling us that this dual unitary property is closely related to entanglement, as I've shown, but also to operator entanglement. You can take these local unitaries acting on this, and this also is a dual unitary operator. So actually, if you look at how does one parameterize dual unitary operators for qubits, it's very simple. It has the following form. So let us consider the one parameter family. So for those of you who are familiar with spin systems, this looks like precisely an Heisenberg model. Okay, there is equal x and this y interactions are equal, and this interaction there's a parameter j. Okay, this is equal when the equal and equal to pi by 4, and this is equal to j. So this is only a one parameter. This is a family of dual unitaries, which means that it satisfies the condition that uj is unitary. It's definitely unitary, but also its realignment is unitary. Um, okay, so for 2 qubits, we have this entire parameterization of dual unitary operators. I must immediately say that nothing, almost nothing is known about general parameterization of qubits. D equals 3 and above, uh, no general parameterization. There are, of course, known examples and families and so on, but no general parameterization of dual unitaries. For those of you who are familiar with group theory, this is related to the difficulty that there is a Cartan form for qubits, but there is no Cartan form for higher dimensions. That is a convenient thing. At least I don't know, and doesn't look like it's very popular. Now, uh, now, how does one go ahead and produce algorithms such that U is unitary, UR is unitary, realignment, which is what I have now said, and also U gamma is unitary, that is partial transpose, so that we create AME 4D states. Okay, so we generalized our algorithms, this nonlinear map. You can also introduce a step where you're doing not only realignment but also realignment and partial transpose. Okay, so you can go ahead, do this, and then do polar decomposition, and then you can continue to iterate this. And we find that this is a very useful thing to do, although it's not 100% guaranteed to lead to AME states, such two unitary or perfect tensors. It very often does. Actually, in dimensions like D is 3, it produces a lot of AME states, or two unitary operators. But in D is the important and unusual thing was D is 6, it was unknown. It took us some time, but this algorithm, along with some other techniques, allowed us to settle this positively. For those of you who haven't seen, there is an article, popular article on this in this Quanta magazine quite recently, because it is connected to a problem of Euler, 36 officer problem of Euler. 36 officers problem of Euler. I don't have time to describe it, but it has connections to combinatorial structures like orthogonal Latin squares, which are sort of like Sudoku puzzles. Okay, and what this finding of such a state is equivalent to finding some quantum solution to the 36 officers of Euler, which is known to be an unsolvable problem classically. I don't think I have time to uh, dwell into that, but maybe I can just pique your curiosity. Maybe Latin square is something like this. Let's take a d by d array. Okay, let's take a 3 by 3 array. 1, 2, 3. Okay, and d elements in this. D elements. So three numbers, 1, 2, 3. I'll just write it out and you will see immediately. 2, 1. Well. 2, 3, 1, 3, 1, 2. Okay, so I have written this 3 by 3 array, and you can see that there is no repetition along a row or a column. So such a thing is a Latin square. Now we can write another Latin square, 1, 2, 3. 2, 1, 3, 2, 3, 1. This is also a Latin square. Okay, and you can put them both together. Just superpose them. You'll have 1, 1, 2, 2, 3, 3, 2, 3, 3, 1, 1, 2, 3, 2, 1, 3, 2, 1. And you see that all possible 9 pairings are there in this. So if this is the case, then it's said to be an orthogonal Latin square. And you can create absolutely maximally entangled states from this orthogonal Latin square. Let me do it immediately. You will see for Q-trits. This is now, we'll now consider as if D is 3. I'll now write the state 1, 1, 1, 1, which is coming from here. This is the 1, 1 matrix element of this 3 by 3 matrix. I will write 1, 1 first, and then the entry 1, 1. Plus 2, 3. No, let me take this one. That is 1, 2. I'm sorry. 2, 1 matrix element. Second row, first column, and entry is 2, 3. You see what I'm doing? And then let's take this, for example, 2, 2, 3, 1. So now you can write the state. This is a state of 4 Q-trits. And because this forms an orthogonal Latin square, this forms an absolutely maximally entangled state 4, 3. So this is related to the story of these orthogonal Latin squares. And the fact that this dimension was open is because Euler conjecture, and it was proved later that in dimension d equals 6, there exists no orthogonal Latin square. So what we showed using these algorithms and nonlinear maps is actually there exists quantum algorithms, quantum states in which such a thing does exist. And therefore, it's some kind of quantum orthogonal Latin squares. Okay, so I think that's a lot. So let me stop here. Let me wind up. What I've been trying to tell you is, first of all, I started with maximally entangled states of just 2 particles and said that it's connected to a unitary operator. And absolutely maximally entangled states of many particles, n particles, each of dimension d, is connected to what are called multi-unitaries. In particular, I gave you the example of 4, d, which is an important case, where you have 2 unitaries or perfect tensors of 4 indices. And you can generate them using some algorithm or dynamical system, which is taking you from unitary matrices to unitary matrices. This is not fully understood, but it was actually very fruitful for us to find out in cases like AME46, where known combinatorial constructions don't work, this dynamical system construction worked, for example. So I gave you this. I can't write down, you can see our paper on the 36 entangled offices. It's basically finding a 36 by 36 unitary matrix with those peculiar properties. Okay, so let me thank you and stop at this point. Thank you very much for your attention.
Thank you,
Hope
Professor.
I piqued some curiosity. Yeah,
Now
thanks.
the session is open for questions, clarifications.
Arul, it has
Yeah.
been a very fascinating talk.
Thank you so much.
Arul. I have some basic doubts. I mean, you wrote the U matrix or U operator for the Heisenberg model.
Yeah, this one.
In terms of e power I.
Yeah.
I sigma x sigma y.
Right.
Yeah. So the so this is so this is an anisotropic Heisenberg model because you have different.
Yeah, that is.
That's a
Yeah. So you can interpret it like that. So the origin why I wrote this was that actually any 4 U4 can be written in the form U1 tensor U2, and this is the Cartan form V1 tensor V2, where these are 2 by 2 unitary matrices. Okay, and this is that form which I wrote. So it is of the form e to the I in general C1 sigma x tensor sigma x, C2 C3. So this is true in general for any U4. In particular, if this is a dual unitary, then C1 and C2 are pi by 4. That's why that particular form I wrote.
And what is its realigned form U of R?
It's actually very, uh, let me tell you in a minute. Give me a, oh, sorry. Okay, so actually this can be written in terms of, it has some kind of an X structure. I'm just trying to see it's there in our latest paper.
So you have a method to evaluate it.
Yeah, I mean, so it's got something like this, some A, B, C, D. So it's got a structure like that. Uh, some B prime, D prime, C prime, something. I forget, something like that. Okay, and this is nothing but in interchanging of these two. So in terms of this thing itself, there is a it yeah. So
Okay, so you have a method to write it down. So,
yeah,
yeah, okay.
yeah. I'm blanking out on that. Yeah.
Okay. Okay, very fine. Thank you very much. Thank you.
So, any other question? Questions from students? Yes, Sasi has some question.
Hi.
Oh, Shashi, hi.
Hello, sir. I mean, in the second part, when you are generalizing for the Ame state, so just like you were finding the nearest unitary, is there something along the line for transpose as well? I mean, or it is just the nearest unitary? I mean, you do the transpose and then find the nearest unitary and just carry on with the
Yeah.
algorithm.
So if you want to find matrices such that U and U partial transpose is unitary, you just replace R instead of R. You replace partial transpose. That also works. So
Okay.
yeah, but in general, the convergence and so on is not proved for this algorithm.
Yeah, actually, that is my kind of next question. How do you kind of attempt for the convergence? I mean, like
Yeah.
how to
So
see it in a
no, I mean, so this is not clear at all. So there exists other fixed points, and especially lower dimensions it works, but higher dimension, like for example, I think we can prove convergence for D is 2, D is 3. Almost everything converges, but we know that there exist fixed points which are not of this kind. So that's why the AME 4-6 problem was not so easy, although the algorithm was there. But by the way, I mean, this is only finding out those which are such that U and U gamma are unitary. You need also U and U gamma as well as UR to be unitary. So there we
right?
use this combination gamma R. So what we showed is that if you have the map in which you have gamma R, then two unitaries are fixed points of the cube of the map. So they are period 3 orbits, because indeed you should have something such that you are commuting, you're going from u to u gamma to ur under this mapping. So it's actually a period 3 fixed point. Um,
Okay.
so yeah, so but in general, these algorithms are not. So there's been some work before ours by Nechita. You can take a look at that. He has done some work on these things. In fact, he calls these things generalized synchron kind algorithms. We didn't know this when we published it, but so maybe this gives you some idea of these some words to. But I mean, it's really open, as I said. To study such a dynamical system on the space of unitary operators, um, in terms of what are the fixed points, what are the convergence rates in general, what is the basin of attraction. So you can have a lot of dynamical systems based questions. They all seem more or less open.
And probably you mentioned, but is it like commuting that first I do u transpose ur, or u transpose, I will end up with the same thing?
No, not necessarily. You're asking if gamma and r commute, is it?
Right, right, right.
No, they don't commute, but it doesn't lead to anything very different, because actually there is a interplay between this gamma realignment and the swap. So they will all be related to each other one way or the other. Uh, so these are really the only unique permutations that you need for a for a four-party state. But now, you suppose you start attacking more number of parties, 6 parties. Then you have more such. You have many more. I think you have 10 such rearrangements to consider. So the next open problem, by the way, those of you who are attacking, is AME 8.4. 8 particles, local dimension 4. It's not known whether it exists or not. And yeah, I can go on the automations now.
Okay, thanks.
Thank
So,
you.
other questions? Any other questions?
Yeah, can I just ask a quick question?
Yes, I.
Yeah, so what I was wondering was this nonlinear map again. I just want to bring up, I don't know that this is a well-posed question, but I'll ask it anyway. You know how there was this conversation about the relationship between classical dynamical maps and quantum unitary transformations are basically and unitary dynamics, and somehow the argument was that if you have this kind of stretching and folding maps, basically, then they tend to kind of really scramble the quantum state all over the place. So this is useful for entanglement generation. And there's all of this work that Prosen is also involved in, and so on, and so for various directions that they're taken. So I was just curious, do you have an intuition on how to think about this nonlinear map? Like, is it, if I was to just think of it as a classical discrete dynamical system, then do you have any additional kind of comments?
No, it's a good question, but no, actually, I don't. I don't have. You are asking whether there's a classical equivalent of such a map that we are.
Or if it's doing something structurally, in the sense that you know how this argument is typically that if you have a bifurcation, then you have orbits going in separate ways, and this kind of.
Yeah. No, actually, no. You see, you don't want this map to be a scrambling or a chaotic map. In fact, if you look at it in this for case of qubits, this Cartan form, there is this so-called Weyl chamber, which is this space of the C1, C2, C3. So in this one, it's actually a contracting map. So what? But there are different rates depending on the C1, C2, C3. But actually, if you start from anywhere in interior, there is one line which is what we are interested in. For this is, let's say U is such that UR is also unitary. Okay, so the dual line. So what we found, and we have proved partially, is that every point gets attracted to this line of fixed points. So there's a line of fixed points here. So you don't want this particular map because you want it to tend towards some particular subsets in the space of unitaries. So it's not, you don't want it to be scrambling. So
And this is about a unity. So it's at a given time you want it to do something.
yeah, I mean, so I haven't thought about the dynamical system itself as a time evolution of
Exactly. Yeah. Exactly.
kind of thing like that. But so the so no.
Sure. Yeah. Thank you. Yeah.
So any other questions? So I think if not, let me thank Professor Arul Lakshminarayan for accepting our invitation and giving a very wonderful talk in this forum. Thank you very much, Professor. Thank you.
Thank you so much, Professor Sendil, and thank you for the opportunity. And I hope that it was useful. Thank you so much.
Thank you. I will write to you. Okay.
Sure. Thank you. Bye, everyone. Bye, Professor Lakshman, Sai, Shashi, and all the students. Bye.
Bye.